Hello, everyone, and welcome to today's webinar, Method Optimization and High Throughput Purification for mRNA and rAAV. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Sartorius BIA Separations. To learn more, visit biaseparations.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. And with that, I'd now like to welcome our speaker, Marco Narobe, Product Manager, Exosomes, Enveloped Viruses, and High Throughput Solutions at Sartorius BIA Separations. For a complete biography on our speaker, please click on the Presenter tab. Marco, thanks for joining us. You may now begin your presentation.
Thank you, Kylie. Hi, ladies and gentlemen. I represent the latest addition to our portfolio, the C-monolithic plates, and how can they be used for method optimization and high throughput purification of different target molecules. So I will begin with our technology, so our monolith technology and how we couple them with the monolithic plates. So the monoliths are, or convective interaction media, are the backbone of our technology. So monolith as a chromatographic media are a single unit structure with highly interconnected channels that are evenly distributed throughout the entire bed. We can make them in 1.3, 2, or 6 micrometers in diameter, and a void volume between 60 and 65%. Some of you may already know monoliths through our column format, where we have radial flow path, and now we couple the monolith with the plate format, where we have the axial flow format. So monolith as a chromatographic media have some key feature that distinguish them from the rest of the world, the chromatographic media. So as I said, they are a single unit structure with channels throughout the entire bed. On average, every channel in the monolith continues in 16 other channels. There are no dead-end pores inside our monoliths. So that means that what you load should come out because there's no entrapment of solids. Due to the channels, we get even flow and distribution when we operate the monolith. And the surface area of the monolith provides the binding sites for your target molecule. Due to channels, the flow through the monolith is convective. So every mass that goes in is exclusively convective. That means the convective flow offers independent resolution and capacity independent of flow rate. That means that what you develop on the plates can easily be transferred to the column format or larger plates. Here we have an example when we did the test between monolith and a standard porous particle. We tried on a column format 3 different flows, loaded the column on the monolith, loaded the target molecule with 3 different flow rates, and at 3 different flow rates, the breakthrough curve came out at the same time. With the porous particle column, the faster we ran the column, the lower the binding capacity was. So that means that convective mass transfer allows binding capacity and resolution to remain unaffected by the change in the flow rate. And we coupled this, our unique monolith technology, with the plate format because we are a column manufacturer and we develop processes for ourselves and for our clients as on various target molecules. And we have found out that we always need to make a balance between an optimal process where we can, let's say, spend a lot of resources on and time, or a little suboptimal process there where we lose less time, but this suboptimal process can bring its own long-term consequences. So we have decided to put the monolith inside the plates. This way we can make design of experiments, we can test different chromatographic conditions, and once we determine the conditions on the plate, all of them can be ran simultaneously. So as a tool, monolithic plates are an ideal starting point for process development, where we can easily screen different chromatographic conditions, or if those are already set, we can use them for high throughput purification of multiple small samples in a single batch. So what are the key features of our well plates? So they are a standard plate format, so they are manufactured according to ANSI/standard. Each well is pre-filled with a defined volume of monolith, thus enabling even flow throughout the plate. The plates, the monolith themselves, have the same chromatographic properties as monoliths inside our large volume columns. So that means what you can expect from a column, you can also expect in a plate. The plate can be operated manually via vacuum manifold, positive pressure manifold, centrifuge. If you have a liquid handler, you can also use that. So automation with the liquid handler is possible. The beauty of the plate is that it's a plug and play format, so no shaking or incubation is required. So once you open the plates, you remove the storage solution according to the instruction manual, and then you can begin your experiment. The plates themselves are also multi-use. You can clean them most chemistries with 1 molar sodium hydroxide, and then re-equilibrate the media inside and store them according to the instruction manual. So how we design the plates? So we have designed the plates from medical grade polypropylene to prevent sticking of our target molecules to the plastics. We elongated the tip of the plate to prevent cross-contamination with the collection plate. Above the tip is the frit that offers support to the monolith, then it's the monolith, and then you have volume for your sample. The plate comes sealed with an aluminum foil, and at the bottom end, it's covered with the also seal. So characteristics of our well plates. So we offer 96 well plates in two different formats, in two different volumes. So 50 microliter monolith inside each well, or 200 microliter monolith inside each well. The 24 well plate has 1 milliliter monolith inside each well. Well load volumes range from 0.9 milliliters in the smallest 96 well plates to up to 6 milliliters in the 24 well plate format. We can operate them with a vacuum manifold with up to 0.6 bar negative pressure and up to 1000 Gs of centrifugation force, or 13 psi of positive pressure. We offer a wide variety of surface chemistries in SIM plates. So we offer different anion exchangers, so strong anion exchanger, quaternary amine, weak anion exchanger, DAE, different cation exchangers, SO3, COH, different hydrophobic, hydrophilic chemistries, so butyl high ligand density, OH, which is our neutral ligand that we use under hydrophobic condition, and our SDVB chemistry. This is a reverse phase chemistry that we use for polishing of mRNA. And then we have different affinity chemistries, different protein chemistries, oligo-DT that is used for purification of mRNA, different mixed mode ligands, so like H-bond ADC, RAAV, those are weak anion exchangers with hydrogen bonding capabilities, or different activated chemistries where the client can bind their own ligand to the monolith on the monolith backbone. So how we use SIM plates in our process development. So we can use SIM plates for evaluating different chromatographic conditions, from sample loading, what are the best binding condition, washing conditions, elution conditions. So we use it for possible applications that we use it are large proteins, so everything that is bigger than IgG, different viruses like AAV, linty, influenza, different virus-like particles, nucleic acids like pDNA and mRNA. So where would we use our SIM monolithic plates? We would use them everywhere in our process where chromatography is used as a purification step. So for the AAV, we can use it as a capture step with the SO3 chemistry. Then later on in the process, we have a polishing step on the QA. We can screen chromatographic conditions for the purification of mRNA. We can use oligo-DT chemistry for mRNA capture step, and then polishing step on the SDVB. The same applies for the pDNA applications. So we catch the pDNA on the DAE chemistry and then polish it on the butyl chemistry. So how we screened different mobile phases for AAV capture step. So we took the 96 cell plate to test which would be the best binding condition for our AAV sample. We tested different pHs, so from 3.5 to 5, different sodium chloride concentrations from no salt inside the sample to 750 millimolar sample, and whether an addition of surfactant played a role in our chromatography. And we did that, and we did everything in triplicates. After the plate was eluted, actually when we loaded the plate, we washed the fractions, and we saw that some AAVs didn't bound, and higher the fluorescent signal, higher the AAV signal inside. That means that if this is in the wash fraction, that means that AAV didn't bind to the chromatography media. That means that it eluted in the flow-through. That means that those were not the best conditions for the capture step of AAV. When we looked at the elution step of AAVs, we saw here also the higher the reading, the higher the concentration of AAV. So here the binding condition was here the AAV bound to the column, but they had different titers and also different impurity profiles. And from this, we did analyzer test to see where we had the highest AAV titer, and we saw that the optimal conditions were buffers of pH 3.5, 0.5 molar salt, with an addition of poloxamine. We also did an SDS page to see our protein impurity profile, actually protein profile, and we see that with the pH 3.5 and 500 millimolar salt, we mostly see the capsid proteins and not much else. And if the pH is too high, we also receive protein impurities inside our sample. So we verified the results, took the best loading buffer, transferred that to our first CMYC disks, then we did a verification on our smallest simultus column, 1 milliliter, and did sodium linear gradient, and we analyzed our fractions for total protein and total DNA content, and we saw that with this we get high virus recovery. We recovered almost 90% of the virus. We removed almost 100% of proteins and more than 99% of DNA. We got a binding capacity of 1.4 to the power of 14 vector capsid per milliliter of SO3 monolith, and in theory we could then load more than a liter of lysate per 1 milliliter of column. We also did binding designing experiments to increase the binding capacity of our oligo-DT ligand. What we did was we took the oligo-DT 96 well plate, did the designing experiments, and screened different factors that could impact the binding capacity, did 84 experiments, and then did two-level screening and used multiple regression model to fit our results and refine them back with the backward selection using a p-value of below 0.05. And with this design of experiments, suggested capacity was of 6 milligrams per milliliter. And we saw this is the different factors that we screened. So we screened different buffers. So 3-phosphate, different pHs, 7.2 to 8, different salts concentrations, different additives. So without additive, urea, guanidinium hydrochloride, arginine, twin-20, different magnesium chloride concentration, and different mRNA concentration. And on the oligo-DT ligand, we get usually under normal condition capacity between 2 and 4 milligrams per milliliter of resin. And this simplified model identified sodium chloride, guanidinium chloride, and magnesium chloride. as a key contributing factors to binding capacity. As a salt, guanidinium hydrochloride demonstrated higher impact than sodium chloride, and with it, we reached binding capacity of 6 milligrams per milliliter. We also saw effect of magnesium that was positive, but it had a less of an impact than guanidinium hydrochloride, and we reached 4.5 milligrams per milliliter. So we verified the results. Those 6 milligrams per milliliter demonstrated in 96 well plates. We transferred that to first our CMYC discs, which resulted in binding capacity 5.5 milligrams per milliliter. We scaled it up to our preparative line, where we loaded the mRNA in 0.75 molar guanidinium hydrochloride, and also achieved 5.5 milligrams per milliliter of mRNA per milliliter of resin. Yeah. And this is my presentation. I hope you will see us as your purification solutions. And now I'm ready to take your questions if you have any.
Great. Well, thank you so much, Marco, for your informative presentation. To our audience, we will now start the live Q&A portion of the webinar. So if you have a question that you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. All right, so let's get started. We've already got a few questions in here. This first question asks, are there any standard protocols provided with these plates?
Not yet. We have application notes and articles that you can use for your own experiments. So those are readily available on our webpage.
Great, thank you. All right, next question here. How many times can we reuse the plate?
This will depend on the sample properties and also the chromatographic steps. So if it's a cruder sample for the capture step, it will be less times, so around 5-10 or maybe even more. If it's a polishing step, it's more than, let's say, multiple times.
Great, thank you. Another question we have here, can a mixed chemistry plate be bought?
No. So we can produce a mixed chemistry plate, but due to the, let's say, manufacturing differences, it would be costlier than ordering 2 different plates.
Great, thank you. And this next question, how long does it take to empty the wells?
So it will depend on the viscosity of the solution and also the chemistry, but usually it takes, for our smallest plate, so 50 microliter 96 well plate, it takes around a minute to empty half a milliliter from the wells.
Wonderful. Well, thank you so much, Marco. This will conclude our session for today. So I want to thank you again for your time and your important research. We would also like to thank LabRoots and our sponsor, Sartorius BIA Separations, for underwriting today's educational webcast. Now, before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. So until next time, take care, everyone. Goodbye.